Last year I found an issue where bringing up the taskbar context menus in Windows was taking too long, about 700 milliseconds for something that should be virtually instantaneous. I grabbed a trace, analyzed it, and wrote a blog post about it, but today I wanted to go through the process in a video of actually analyzing that trace to help people understand how to do this sort of exploration. I've got a lot of traces here. I'm a bit of a pack rat that way, and this is the one. So let's just open this up. All right, so this is basically using the default symbols that come with my UI for ETW tool. So it's got a bunch of different graphs open already. And we need to use these different graphs and the information in them to find out what's going on. But first we need to find out when it's going on. Because this was poor performance that was triggered by input events, we can look at these events here, which are actually emitted by UI for ETW. It's an input logger, keyboard logger, mouse logger, and we can actually find the mouse events which triggered this. So the mouse up events are usually when things happen. So we can look at mouse up, and we can see there's a mouse up on button type 2. So that is the right mouse button, and then shortly after that there's a click with button type 0, the left mouse button, and then again 2 and then 0. So those are the two instances of this. I repeated the test twice, so that's making it appear and making it disappear. And we don't actually care about when it disappeared. We want to know how long it took from when I clicked the mouse button to when the menu actually appeared. And there's some clues in here that can help us figure that out. We can actually see that when I did the initial down click, the mouse down on the right mouse button, that window focus immediately changed. So that's an interesting clue. And then focus changed again. It changed within Explorer, but then it changed again to this shell experience host. I don't know what that is, but if you look at the timing here, it looks like we click, change focus, and then there's a bunch of CPU activity. And then focus changes again. So my guess is that when I release the mouse button, that's when it starts bringing up the context menu, and then when the focus changes, that means it's done. We can zoom in on this. I'm just holding down the control key and spinning the mouse wheel to get a better sense of what's going on. And there's the release of the mouse button. Not much happens for, I don't know, 65 milliseconds or so, and then there's a bunch of CPU activity. So I'm going to assume that when this focus event leaves, then the menu is ready. So I'm going to zoom in on that. And then I'm going to look at the mouse up event, and I'm going to just drag that all the way over here. So now I've selected the time from when the mouse button was released until the focus changed. That is 616 milliseconds. In the blog post I said it was 700. Close enough. It's going to vary a little bit. So I think this is the time frame that we're looking at. I can immediately see that we are CPU bound in runtime broker, the experience host, shell experience host process. I don't know that that's actually the cause, but it's very suspicious, and I'm just going to simplify things by assuming that that's the problem, that we're CPU bound there, so whatever this process is doing is the limiting factor. It just seems like too much of a coincidence for it not to be, so I'm going to skip the step where I prove that it is. Don't need these two graphs anymore. All right, since we're looking at CPU usage, the best graph to explore, the best table actually, is CPU usage sampled. So this is a 1 kilohertz sampling profiler that is actually really good. And we can see it caught 493 samples in the runtime broker Microsoft Windows shell experience host process. Microsoft doesn't believe in naming their threads, which is too bad because it's very helpful. So I'm just going to close off that column. And then we've got a few different threads. pretty much all of the work is in this one thread here. And you can see where the time is being spent in that thread. So we can just start drilling down and see where the time is going. And, you know, it's a bunch of goop, COM stuff, Windows stuff, app invoke. I don't know. I skim past that. And I'm just looking for something interesting. I don't know this code, so it's more tricky to try and figure out what's going on, what should happen, what shouldn't. And I got lucky. It didn't take very long to find something that seems awry. There are 139 samples out of the 449 on this thread in read file. That seems like a lot of time to be spending in the kernel read file function. And then if we go look down at some other areas that are pretty hot, we see pretty quickly even more time being spent in read file. So it's actually being reached on multiple different call paths. So what we can do is right-click and say View Callers by function, and that's going to show us all the time, all the samples that go through this function. And now we see 315 of the 449 samples are going through read file. That's where most of the time is going when we're waiting for that context menu. Okay, that is actually really weird, but it's a little bit worse than that. We can clear that, and then we'll drill down again. And sure, there's this time being spent in read file, but also time being spent in set file pointer. And let's try the same trick here. And boom, 71 samples in set file pointer. So we're now talking almost 400 samples in these two kernel functions for reading a file. Now you might be thinking, wow, must be reading a lot of data from the file. No, that's not what's going on. If this was actually waiting on the disk, then the process would be going idle. We wouldn't be using CPU time. This is CPU time being spent, not disk time. I mean, I've got a very fast disk, so I could read an awful lot of data in 400 milliseconds. But that's not even what's happening. We're probably not even touching the disk at all, or else we would be going off CPU. But clearly there's a lot of file I/O going on here. Perhaps no disk I/O, but a lot of file I/O. So let's go and look at the storage. Let's look at the disk usage first, just to verify that it's pretty much idle. There's a burst here where it's very busy. Turns out that's actually from recording the trace. So that's just an anomaly of the fact that I'm profiling. There's basically zero disk activity. But if we look at file I/O, then we can start to figure out what's going on. We can change the specific graph that we're using, the specific view. Let's go size by file name, process, stack for read-write. None of these table arrangements are exactly what I want, but this one is at least vaguely close. We didn't record stack data for file I/O, so I'll just turn off that column. And I actually want to group by process first. We can look in the system process and see, yeah, there's a bunch of time being spent writing to this ETL file. Again, that's just the tracing going on. But here's our runtime broker process. And, well, now we can start to see what's going on. So there's this file, automaticdestinations.ms, and we're doing 114,000 reads from it. How do I know they're reads? Well, I don't yet, but I can add the event type column, and then we can see, yep, 114,000 reads. We're reading all of 7.8 megabytes of data, which means we're reading an average of 68 bytes each time, and that is simply inefficient. You should be reading several kilobytes, maybe a megabyte or so at a time. And it turns out this file itself is only 4 megabytes. So we're reading it twice over, and we're doing that in a very inefficient way.
So that's the issue. Calling into the kernel, read file, is expensive. And for some reason, the Microsoft code is doing that about 1,000 times more often than necessary. And therefore, it's reading this file in the most inefficient way possible. I'm not sure why they didn't notice this issue, but there it is. To avoid this problem in your own code, just be sure to read lots of data in each call to read file, caching it locally in process as needed. I reported this bug via sarcastic tweet, blog post, and the feedback app, and it looks like Microsoft has fixed it. I think the fix will be shipping in May 2020. If you want to try repeating this analysis yourself, you can find the trace that I recorded by going to tinyurl.com/etw central, going to the Taskbar Latency and Kernel calls post, and then searching for trace of the issue. I hope this was helpful, and let me know if there are other trace analysis videos that you would like to see.